So the valence bond theory connects the shape to the orbital properties, and we usually focus on the center atom, but not always. The model says that a covalent bond requires the orbitals of two atoms to overlap in space. You know, they have to come together and overlap in three-dimensional space, and an electron pair occupies the space where they overlap. That's the essence of a covalent bond as it's described in the valence bond or VB model. So if we looked at dihydrogen, one of the famous 7 diatomics, we can describe the valence bond picture of dihydrogen by writing 2 hydrogen 1s orbitals on separate hydrogen atoms and then imagining mentally that these things are going to come together until they reach the geometry of the H2 molecule. And in that process, there is a mutual overlap between the 2 1s orbitals here. Now remember, even though we draw nice spheres for this, that's not a good picture for a 1s orbital. The electron density just gets less and less dense as you go outwards. There isn't any end to a 1s orbital at all. It does not end any place per se. It goes on in principle to infinity. But if you bring 2 of them together, that will be a significant amount of overlap between their respective volumes. And it's in that overlap that the pair of electrons we write as 2 dots in the Lewis dot diagram resides. And they reside always as a pair, not 2 singles, because of the general ideas that the Pauli exclusion principle holds as well for molecules as it does for atoms. So opposing spins of the electron pairs, opposing spins of the electrons pair. And the Pauli exclusion principle says that the overlapping orbitals have a capacity, a total capacity for 2 electrons. So that limits the number of electrons that can be in the space between the nuclei to 2 for a single bond. Okay? In order to have more than 2, we have to have more orbitals than 2. And that comes along when we talk about pi bonds. The second thing is that as far as the strength of a bond goes, the more overlap you have, the better. Okay? The localization of a pair of electrons to stabilize the HF bond coulombically, we described what that was. 4 attractions, 2 repulsions. We need to get the pair of electrons in there between the 2 atoms and get the atoms at their internuclear distance for this particular kind of bond. In other words, the HF bond distance. So the larger the overlap region, other things being equal, the stronger the bond will be. Right? And you could see I've kind of overlapped this overlap for you here and smeared it so you could see where most of it is. All right? The last thing is if the orbitals in the atoms aren't pointing in the right directions to make this happen, we take combinations of the wave functions of the available orbitals to make something called hybrid orbitals that are pointing in the right direction. And I suspect you heard about hybrid orbitals in your high school chemistry class or in Chemistry 1301 if you took that. And I'll have to come back to that and tell you more about it in a moment. Sometimes it's not necessary. For example, you can find in the F2 molecule that 2p atomic orbitals, not hybrid orbitals, are just fine to come together and form that single bond between the 2 fluorines. Just fine, no problem. But there are other molecules, like methane, where carbon doesn't have the right set, or an optimal set, of orbitals pointing towards the corners of a tetrahedron where we know the hydrogen atoms in this molecule are. So using only s and p atomic orbitals, the description of the bonding is unsatisfying and we would say unsuccessful. So here's where we have to do the hybridization. Linus Pauling, again, had a lot to do with this. And if we take the methane molecule, what he said was that the ground state hydrogen atom, in other words, 2s2, 2p2, is not well suited to form 4 equivalent bonds. Well, here is the isolated carbon atom, and here's the 2s pair right here. Here are 2 single electrons in the 2p orbitals, and this thing looks like it would be pretty good for forming 2 bonds, right? I could bring in a hydrogen and make a bond right there, and I could bring in another hydrogen and make a bond right there. That would produce a carbon that was not octet, however. And that particular molecule exists, but only under very optimal conditions. So this is not a satisfactory description. And Pauling said the valence orbitals in the molecule, in the CH4 molecule, are not the same as for an isolated carbon atom by itself. They're not the same as this. And the valence bond uses mathematical combinations of the wave functions on the atomic orbitals to create new orbitals with better bonding properties. Specifically, I'm going to show you that we will be able to use the Vesper model to predict exactly what hybrids we're going to use. Such orbital mixing we know as hybridization. The mixed atomic orbitals that you get from doing this hybridization are called hybrid orbitals, and I frequently abbreviate them HO. The number of hybrid orbitals always equals the number of atomic orbitals that you mix. So if you mix 2, you get 2, and the other atomic orbitals, if any, are left alone. Something that's more useful than that observation is this observation. The number of electron groups around the center atom, according to the Vesper model, the number of electron groups has to equal the number of hybrid orbitals. Well, that's simple enough. You think about it. The electrons can't be just hanging out there in space. The electron groups have to be in some kind of an orbital, according to quantum mechanics. And I believe that's reasonable to expect. So the idea here is there'll be 1 hybrid orbital for each electron group. And it may be more complicated than that, but that's at a minimum. Okay? So you now have at your command the necessary information to take the molecule, draw the Lewis dot structure for it, and count the number of electron pairs around the center atom. Right? You've done that already. So that will tell you how many hybrid orbitals there have to be. The type of hybrid orbitals varies according to the type of atomic orbitals that we mix. The specific hybrid orbital is determined by what shape it's being made for. Okay? And of course, the shape class is the parameter that we use to connect us to what shape this molecule might have. So I want to focus on the skill of picking the type of hybrid orbitals from the shape class. The shape class is the AXE thing that we talked about before. That's a shape class. We know how to assign center atoms to the right shape class. We've done that before. So I'm going to start with the simplest case that we did in the Vesper model. So everything will be as easy as possible. And that is the AX2 case, where we have just 2 electron groups. And the electron groups would be, for example, in this BeCl2 gas molecule that we looked at, they would be 180 degrees apart, and that would account for the repulsion dictating the shape. In other words, the 2 pairs of electrons, according to the Vesper rule, would be allowed to get as far away from one another as possible, and that would be 180 degrees apart in a linear shape. So for the hybridization for these 2 electron groups, we need to have some kind of hybridization that points at 180 degrees apart. Two hybrid orbitals pointing east and west. Okay. Now, one way that we can do that is to mix a valence s atomic orbital wave function with a valence p atomic orbital wave function on the center atoms. And since we mix two atomic orbitals, we'll get two hybrid orbitals. They will be equivalent. Their name will be SP because we used one S and one P. And when you do the mathematics, and it's pretty easy. I don't think there's anyone in this room who couldn't do the mathematics if it was needed and we had time to devote to it. You get the orientation of these two SP hybrid orbitals to be 180 degrees. We can see it pictorially. I'll show it to you in a minute. Before we do that, let's look at the energy level diagram that we have up to this point. Here is, for example, if we look at the BeCl2 case, here's an isolated beryllium atom's valence. Its electron configuration is 2s2, 2p nothing. Okay? So there's a pair of electrons in the 2s orbital in the isolated beryllium atom and nothing in the 2p. If you follow Pauling's approach and you mix the s and p orbital wave functions, you get two sp hybrid orbitals. And you have left over two p atomic orbitals that don't participate. Okay? So what I'm telling you is if you do this mathematics and you look at the wave function of these two sp hybrid orbitals, one points east and one points west. You could sort of look at it this way. If we look at the 2s and the 2p and we mix them, if we take the sum of them, we get one directionality, for example, west with this one. We take the difference, I guess it's the other way. If we take the sum, they go this way, the sp hybrid points east, and if you take the difference, it goes west. Well, the best way for us to do this is to simply think clearly about adding the wave functions for these things and not really do it mathematically. Well, now the result of this, if we put these two together, does show that there's a big lobe pointing east and can form a bond with somebody out that direction, and one going west. But it's rather hard to see it if you do the actual shape of the sp hybrid. So we'll throw that out. And we're going to make simplified view of hybrid orbitals. We're going to make a hybrid orbital look like maybe a p orbital, one side of which is very large and the other side very small. Okay, and the reason for that has to do with the effect of the s, but let's not go there. So the two sp hybrids, one looks east, this one, and one looks west, and it can form bonds with whatever's out that direction, and that will cause the molecule to be a linear molecule. So if we go back to our energy level diagram, here's 2s2, 2p nothing for the isolated beryllium atom, and if we mix them mathematically, they produce two sp hybrid orbitals. Since there's two electrons and these orbitals are equivalent and have the same energy, we'll put one electron in each one in order to follow Hund's rules. Hund's rules still apply. So we have two orbitals, same energy, put in two electrons. The idea will be to fill each one halfway and have parallel spins. And here's the 2p atomic orbitals up here that are sort of ghostly companions. They're not really doing anything. So at this point, we have the beryllium atom already. It's prepared, it's hybridized, and it can form a molecule. It's got electrons in each sp hybrid, so what will happen? Okay, here we are again, just what I said. Here's the beryllium, and it's got the two sp hybrid orbitals on the right side and the left side, the east side, west side, whatever. Each one has one electron. Here's the one on the left. There's the one on the right. All it has to do now to form BeCl2 is to bring in the chlorines, let the p orbitals on the chlorine overlap this one and this one, and I still have the ghostly unhybridized 2p's there. I won't say more about them. We bring in the chlorine 3p, that's the valence orbital on chlorine that has an unpaired electron. We bring one on this side, one on that side, and we let them overlap. And when they overlap, according to the valence bond model, they form a pair of electrons in the overlapping region between the two, and that's a beryllium chloride single bond. And there'll be another one over here. So what you've just seen is the creation of hybrid orbitals that support the linear shape. And they are called sp hybrid orbitals. In the energy level diagram, what I like to do for the clarity of my own thinking is I write the sp hybrids down the way I did over here with one electron each from the beryllium, and then I bring in the chlorine with its unpaired electron here and the one over here, and I form the bond right there. So if you look at this bond right here corresponds to that pair of electrons in the energy level diagram, and this one corresponds to that, or vice versa. So that completes our description of BeCl2, and it was AX2, I remind you, AX2, and that told us to use sp hybrid orbitals because, as we came to see later, they had the right properties. Questions? All right, if no questions on that, let's go ahead to a case that has 3 hybrid orbitals. And in that case, if there are 3 electron groups around the center atom, and if you remember BF3 was an example where that happened, then we hybridize one s atomic orbital and 2 p atomic orbitals on the center atom to give 3 sp2 hybrid orbitals. They are equivalent, they have the same energy, and it turns out that they point toward the directions of an equilateral triangle in a plane. And that's just what we need for BF3. If you think about the boron atom in BF3, here it is, and it has fluorines at the corners of an equilateral triangle in a plane. BF3 is planar. If you remember from the Vesper approach to this thing, BF3, what is the shape class of boron in BF3? Anybody remember? 3 electron groups around it, no lone pairs. That's the shape. What about the shape class? A what? AX3. Good. AX3 leads us to sp2 hybrid orbitals. And sp2 hybrid orbitals are shown over here in the energy diagram. We mix a 2s and 2 2p's, and we get 3 equivalent sp2 hybrids. Here they are marked in orange, and since there are 3 electrons, Hund's rule says there has to be 1 unpaired electron in each one. And this 2p out here isn't used. So now what we're going to do is to bring in the fluorines. Each fluorine has 1 orbital with an unpaired electron. It's a 2p. We'll bring them in so that they will overlap with the sp2 hybrids on boron that also have 1 electron each. And so we bring in 1 fluorine. Here's its electron. We make a pair. So if you look at this, this might be that pair of electrons right there. And then we look for another one. And this fluorine to boron bond might refer to that. Now, if you were asked to name or describe the BF bond in BF3 according to the valence bond model, here's how you would do it. You would write down boron, and then the orbital that it uses to form these bonds is sp2, and then you would write down what's bonded to boron through sp2, and that's fluorine 2p. And of course, there are 3 of them. The third one is that one right there. So you can depict the bonding using the energy level diagram, or you can make a sketch of it, or you can actually write down the description of the bonds. All of those things come from the valence bond description here. Does this make sense to you? Okay. I hope it does. Hope it does. Now, the same sp2 hybrid orbitals can be used for any central atom that has 3 electron groups around it. So AX3 is one of them, but it could also be AX2E, for example. And in that case, one of the hybrid orbitals would accommodate the lone pair, the E. That's perfectly all right. A hybrid orbital is happy with a lone pair of electrons, just like a bonded pair of electrons, according to this model. Okay. Questions about AX3 and AX2E hybrid orbitals? All right, let's go on to the next one then. If not, AX4. If you have an AX4 case, you need 4 hybrid orbitals. And what you need to do is to mix all of the p orbitals and the s orbital for the center atom. Okay? An s and 3 p's is 4 atomic orbitals, so you're going to make 4 hybrid orbitals. I just thought you might like to see what a wave mechanical picture of the orbital that you get out of this, which is, of course, an sp3 hybrid orbital, what it looks like. This picture over here is a quantum mechanical diagram of the cloud of electrons that makes up an sp3 hybrid orbital. And don't worry about the colors changing. There is a tail and there is a head to these things. And the bonding takes place through the head here. You can sort of see it like that. This is the bonding part. This is the tail. Okay? So these sp3 hybrid orbitals, there will be 4 of them. Yes?
The notes, the printed notes, say in that blue box at the top, say 2s plus 3, 2p. Are these printed notes right, or is that right?
It doesn't matter. They're both right. We're mixing 1s and 3p. They could be 2p's or 3p's or 4p's. It doesn't matter as long as there's 3p atomic orbitals. I actually changed that this morning because I didn't want you to think it had to be 2p. And that provoked a good question, so thank you. All right. If we look at carbon again, we discussed this before a little bit, we need 4 bonds pointing towards the corners of a regular tetrahedron. 4 bonds means we have to mix 4 atomic orbitals, and we'll do that with the s and the 3p atomic orbitals on carbon, the valence ones. So if we look at this first, we note that there are 4 electrons. They're the valence electrons of the carbon. And according to Pauling, we mix these 4, and we get 4 equivalent sp3 hybrids. The symbology here is, I hope, clear-cut, an S and 3 Ps. Now, with 4 electrons, and following Hund's rules, we put the carbon electrons, 1 each, spins parallel into the 4 sp3 hybrids. Now we're ready to form bonds here, and we can bring in a hydrogen and its electron, and we can make a CH bond. We would describe this in writing how? How would we do it? Carbon, sp3, hydrogen. What's hydrogen? 1s. Carbon sp3, hydrogen 1s. That's the valence bond description of the bonds in methane. And a couple years back, that question was on the MCAT exam. And I was surprised. So that's 1 CH bond. Here's another. Here's a third. And there's the last one. And these then overlap as shown to form electron pair bonds. And notice the carbon sp3 hybrids are pointing towards the corners of a tetrahedron. There they are. And each one has a hydrogen 1s overlapping, forming the appropriate single bond. One pair of electrons shared between the two nuclei. So we have accomplished what we wanted to do. We wanted to take the shape, which is tetrahedral, and provide tetrahedral bonding. And that's what sp3 hybrids do. It's kind of cool, I think. It's not the answer to everything, but it's a simple answer to many things. Okay. We could use sp3 hybrids equally well for anything that has 4 electron groups around the center atom. Something else that does, of course, is ammonia. AX3E is the shape class for the ammonia. And an isolated nitrogen atom would have the electron configuration shown here, 2s2, 2p3. And that would not work to form ammonia, because what would be the bond angle between any two of these 2p atomic orbitals? Anybody remember? Between the atomic orbitals, p orbitals. So we have one that's pointing up the z-axis. Where's the next one pointing? Haven't heard it yet. 90 degrees, x-axis. And 90 degrees again, y-axis. They would all be 90 degrees apart if we use them for the bonding. But the shape of ammonia doesn't have 90-degree bond angles. It has 107 and change degree bond angles. So this combination here doesn't work. It's better if you have sp3 hybrids, which are at 109 degrees, much closer to the actual bond angle. And later we'll get a chance to talk about why it's not right exactly on 109.5 degrees. So here are the 3 hydrogens. Here are the bonds that they form. And here's the ammonia molecule. Notice one of the 4 sp3s just houses the lone pair that we know exists on ammonia, on the nitrogen. And the other 3 form 3 sp3 hybrid bonds. Each one would be nitrogen sp3, hydrogen 1s. Now in the water molecule, we have AX2E2. That's 4 electron groups. So we will use sp3 hybrid orbitals on the oxygen to account for the 4 electron groups, right? 4 electron groups, 2 X's, 2 E's. All right? So lone pairs will fill 2 of the hybrid orbitals in this case. Up here we had lone pair filling 1. Now we're going to take the same 4 sp3 hybrids built on an oxygen atom, which is described over here, and 2 lone pairs will occupy hybrid orbitals, and then the last 2 electrons out of the 6 will be spin paired in the other 2 sp3 hybrids. Okay? So if we bring in a hydrogen, like maybe this one right here, and overlap the 1s with the sp3 on oxygen, then we make an oxygen sp3 hydrogen 1s single bond. And we can do that again with the other hydrogen, and we'll form another oxygen sp3 hydrogen 1s single bond. So the H2O molecule shows 2 OH single bonds and 2 lone pairs, and they're all based on sp3 hybrid orbitals. Again, the angle for water is not perfectly 109.5 degrees. So later we're going to have to try to rationalize why it's a little bit different than the sp3 hybrid orbitals would suggest. Questions on ammonia and water? Okay, comfortable with that? Cases where you have an expanded octet. And we looked at 2 of those, 5 electron groups and 6 electron groups. So let's start with 5 electron groups. AX5 central atoms are always from period 3 or higher. So we said that it is potentially possible that d orbitals could be mixed or could be involved in the bonding for these molecules that have a central atom that exceeds the octet. The reason something can't exceed an octet is if it only has s and p orbitals available, it can only accommodate 4 electron groups, period. But if its z is 13 or above, then d orbitals can be mixed in to these hybrids. And in fact, the AX5 case and every other case that has 5 electron groups can be described by sp3d hybridization. Sometimes this is written dsp3. Both of those are equivalent, according to me. Okay? So if we look at a molecule that we've looked at before, PCl5, we can make 5 hybrid orbitals to accommodate the chlorines, which we know to be in what shape? In PCl5, AX5. What shape is that? Trigonal bipyramidal. Good, good. So AX5 shape class is indicative of a trigonal bipyramidal shape. So what we need here is 5 hybrid orbitals that point in the direction of the 3 axial chlorines and the 3 equatorial chlorines and the 2 axial ones. Okay, so we'll start with an isolated phosphorus atom over here. Phosphorus is in group 5. Its valence electron configuration is 3s2, 3p3. And what we're going to have to do now is to mix the 3s atomic orbital, the 3p atomic orbitals, and 1 3d atomic orbital to make dsp3 hybrid orbitals. So when we do that, the 5 sp3d or dsp3s are equivalent. They are equivalent in energy. That's what I should have said. They're equivalent in energy, and so if we put 5 electrons, 2 and 3, 5 electrons in there, Hund's rule says there'll be 1 electron in each one, and their spins will be parallel. Okay? So that's a very good situation to form 5 bonds. And here is the orbital description. The hybrid orbitals are in purple around the phosphorus, 1, 2, 3 equatorial, 1, 2 axial. And what we can do is we can bring in then the 5 chlorines. Here's the first one. There's second, third, fourth, and fifth. And they correspond to each one of these phosphorus-chlorine bonds. So if we needed to describe the phosphorus-chlorine bonds, according to the valence bond model in PCl5, it would be P sp3d or dsp3 dash Cl, and what would the Cl be? Chlorine is in the 3rd row, and therefore it would have it would have hybrid orbitals using 3p atomic orbitals. So this would be, it'd have atomic orbitals using the 3p. So this would be phosphorus sp3d chlorine 3p. Sorry, I got my tongue tangled up. So that accounts for the formation of 5 bonds in an AX5 case. Are there questions about that? Now, this sp3d hybridization will apply to anything that has 5 electron groups around the center atom, as before. So that would work for SF4, where you had an AX4E, or something that, a T-shaped molecule like BrCl3 that had 2 lone pairs and 3 bonding pairs. That would work. Okay, the last case, AX6, is a version of the expanded octet that requires 6 electron groups. In AX6, the center atom is required to have 6 hybrid orbitals that are equivalent. And in something like sulfur hexafluoride, which we've given before as an example of expanded octet with 6 pairs of electrons, the valence bond model chooses the center atom, in this case the sulfur 3s, 3 of the sulfur 3p's, and 2 of the 3d's to form 6 equivalent sp3d2 hybrid orbitals. So here's an isolated sulfur atom, S3s2, 3p4, and there's 2 3d's up here that we're going to mix in. No electrons in them at the beginning. So that would make 6 sp3d2 equivalent hybrid orbitals. Hund's rule comes in and says, whoa, you got 6 electrons, you got 6 orbitals. They're all going to be parallel spins, all 1 electron in each one with parallel spins. So again, we could imagine that we could form 6 bonds just by bringing in the available, in this case the fluorines, and make a bond by overlapping and making a pair of electrons. So we would have a fluorine like this, and we would make a sulfur fluorine bond, and so forth. And this would end up making an octahedral structure, and the sulfur has now 6 equivalent sp3d2 hybrid orbitals, and each one forms a single bond, and that each one would be called a sulfur sp3d2 fluorine 2p bond. Okay, how are we doing here? Does this fit together for you? Does it seem plausible? Maybe? Yes, go ahead. Chlorine?
Yes.
Mm-hmm.
Would it be 3p?
Yes, it would be.
Okay.
It would be 3p. If it were bromine, it would be 4p. It's not going to be bromine. However, 6 bromines are too big to fit around the sulfur. Fluorine works well. Okay, table 11.1 summarizes the different hybridization types from sp to sp3d2, and you need to commit that to memory. Okay, I want to go through a couple of cases that have some complications to them to be sure that you see what needs to be done. So describe the mixing of atomic orbitals on the center atoms to give hybrid orbitals in these 2 molecules, methyl alcohol and sulfur tetrafluoride. Now, we've looked at these before. We've drawn their Lewis dot diagrams, and we've drawn their shapes and so forth. And remember, we start with the molecular formula. We create the Lewis structure, Lewis dot structure. Then we determine from the electron group arrangement what the molecular shape is. And now, from table 11.1, we take the last step and make the hybrid orbitals. So, methyl alcohol has a Lewis dot structure that looks like this. It has 2 center atoms. It has a carbon that has 3 hydrogens and 1 oxygen. So, that carbon is AX4, right? 4 electron groups, it's AX4, no lone pairs. Okay? And the oxygen is, it has 4 electron groups. It has this bond, carbon-oxygen bond, the hydrogen-oxygen bond. It has 2 lone pairs. So both of these central atoms correspond to 4 electron groups, and therefore they use sp3 hybrid orbitals in both cases. So in the description of this thing, if we start with the carbon, again, 2s2, 2p2 doesn't work for this molecule. So we hybridize all of the s and p atomic orbitals. We make 4 sp3 hybrids. We put the 4 electrons in, and then we have everything we need to form 4 bonds. 3 of those bonds are going to be to hydrogen. Okay? And those are just like we had for methane. What is the 4th bond? It's this bond to oxygen. So oxygen is going to use an sp3 hybrid as well, and this bond between the carbon and the oxygen would have a special designation because of that. It involves 2 hybrid orbitals. And so what we could say is this bond right here is a carbon sp3, and oxygen, sp3. Okay? And we could describe each one of the bonds that way, and we could say what hybrid orbitals the lone pairs are in. We could do all that with this model. And I'll leave that for you to think about. And there's a little picture of the thing, ball and stick model. Now, if we look at the oxygen end of the atom, as we said, it has 4 electron groups, 2 of which are lone pairs. And so if we start with the oxygen atom by itself, it's 2s2, 2p4, 6 total electrons. So if we mix these, we make 4 sp3 hybrids, and we fill them up in the usual way. We put in this electron, this one, and then we pair up that one, we pair up that one, and that gives us 2 lone pairs, of course, and we can make the OH bond, this guy right here, you see him? You can make the OH bond by sharing his electron with an oxygen sp3, so we could write that down. And then we have the carbon on the other side, and of course that's just the other end of the carbon sp3, oxygen sp3 bond. So this describes all of the bonds in methyl alcohol. Does anyone have a question or a comment about it? Remember, we have to have a Lewis dot diagram. We have to count the electron groups and so forth. Well, let's look at SF4. I mentioned it before. If you draw the Lewis dot diagram for it, there's a pair of electrons on the sulfur. So that means the sulfur has 4 bonding electron groups and 1 lone pair. So that'll be an AX4E, which, if you recall, is a seesaw structure. And the sulfur atom has a total of 5 electron groups. And if it has 5 electron groups, we need 5 hybrid orbitals, so that means we're going to use sp3d hybrid orbitals. Now, I made this little table for you. If you have a hard time figuring this out, you can memorize this table. 2 electron groups, sp, 3 electron groups, sp2, 4 electron groups, sp3, and what we need is 5 electron groups, so that's sp3d. Okay? So as you look at this thing, we have, as usual, the sulfur here will have 5 orbitals. 4 of them will be used to bond, single bonds to the fluorine. 1 will be used for a lone pair. Here it is as a sulfur atom, as we saw before. We now mix them. We make 5 sp3d hybrid orbitals nicely together, the way you see them there. And we count the electrons, 2, 4, 6. So we put in 1, 2, 3, 4, 5. Then we pair that one up. And this will be the lone pair here. So this will be E. And then we will bring in fluorines. And we'll make sulfur-fluorine bonds in the usual way. It's sort of like a molecular toolkit. Right? So you can describe every bond in there. It works pretty well. Pretty well. Okay. Last thing I need to do today is to tell you when not to use hybrid orbitals. Right? We've seen many examples of when to use them. I've done all this. When do you not need them? Well, hybridization is generally needed whenever the shape doesn't match up to the shape of atomic orbitals that you could get from atomic orbitals. And frequently, that has to do with molecules whose central atoms are surrounded by atoms that are crowded to some degree. If they're not crowded, in other words, the center atom is a sulfur instead of an oxygen, then the bond angles that you see for a large atom in the center are frequently not in the range of hybrid orbital bond angles. H2S, for example, the bond angle is 92 degrees, which is almost perfect for two atomic orbital, p atomic orbitals forming the bonds. So that's a perfectly adequate description, and if you came across a question that said describe the bonds in H2S, it would be perfectly good to say there's sulfur 2p, hydrogen 1s. I'm sorry, sulfur 3p, hydrogen 1s. And the bond angles can be your guide. For hydride compounds in particular, H2X and H3X and so forth, the ones that have bond angles near 90 degrees, and that's always large central atoms, you don't need to invoke hybridization. I've put you a list of a few here so you can see what they're like. The bond angles are near 90 degrees and therefore no hybridization.